Okay, let's start our new topic, which is estimation. Till the end of the semester, we will cover topics related to the estimation. But first, we start with point estimation, and you will see two new estimation techniques. One of them is the method of moment estimation. The other one is the maximum likelihood estimation. In the literature, there are other estimation types, but these are the most well known and still used methods, especially the maximum likelihood estimation. So we will talk about all the logic, what is likelihood, what is a likelihood function, why we try to maximize it. So we will give all these details. But we will start with a simple one. Method of moment estimation. Here you have to know how to find the moments and central moments. It has a very simple logic actually. Point estimation. Okay. So in the point estimation, so we assume that we have a random variable, and we know its PDF form or PMF form. Okay, so this is the population distribution function. Okay, so in many cases, basically, experimenter is not able to specify the PDF completely. What we mean by specifying the PDF completely, so if we have a PDF f of xt, whatever that is, maybe we know what distribution it follows, but this parameter is unknown. We can see that, okay, so it could be a right-skewed distribution, and it seems like it's kind of a gamma PDF. Okay, so it's gamma, but we don't know which parameters, which alpha and beta parameters create that sample. So we have to look at the data generating mechanisms here and try to find which specific parameters should give this specific distribution. So it may be possible to assume a PDF is a member of some known family. So we can say that, okay, so we have this one, but it is a family of, let's say, normal PDFs, normal distribution. Or we can say that it's a family of gamma type. So after deciding that, actually, we need to specify, we need to find specifically which distribution creates the sample. So how we can do that? By estimating theta value. Okay, so for normal, actually we usually focus on normal, but our samples not most of the time normally distributed, it doesn't follow. So if this is the case, so then how can we represent an unknown parameters using our sample? Is always, do we have to always use x bar, always use sample variance, or other things, minimum values, maximum values, range? So we need to decide how can we represent this unknown parameter using sample information, and how can we be sure that this statistic actually very close to the original population value. So basically here our main objective is assigning an appropriate theta value. Appropriate value for theta based on our observed data sample from the population. Okay, so our main objective is this one. And we will see how can we create estimators, how can we develop estimators for certain known distributions. And we will see that actually not all theta represented by x bar. So we will see actually how we can find these estimators for any given distribution. So we start with point estimation, then we will enlarge our estimation in the next semester. So to be able to do that, basically, we need to Okay, we need to use statistical inference, right? Okay, so how can we assign this appropriate value for theta using our sample observations? So this is our statistical inference topic. So determining certain unknown properties of a probability distribution on the basis of a sample. And usually we assume that we have a random sample because then each sample item is independent from each other and they are identical distributed. So if our sample is random sample, then our calculations are much more easier. If we can satisfy this randomness, it will be very easy for us to do the calculations. Otherwise we have to deal with dependency between the observations. Okay, so I'm using Word this time. I hope I can switch to the next page easily, I hope. Okay, so this is my first time using Word in iPad. So we have unknown parameters. So our aim is to be able to estimate those estimate parameters using sample information. And also we will see that we might have many different estimators for the same unknown parameter. Then we have to, our question will be which estimator that I have to choose to represent theta using my sample information. So we will see then the good properties of estimators, and then we want to use those properties and try to choose the best estimator for our unknown parameter. So our estimation problem has three categories basically. One of them is just the simple point estimation. So basically here what we are doing, let's say we have an unknown parameter mu, we want to estimate it, and using the sample information we calculated its value. Okay, so it's 8, just it. We try to find it numerically actually. So when we have a sample, how can we estimate this parameter? Let's say sample mean, sample median, some function of a sample mean, whatever. So we will see that. Then when we just take one sample, basically sample to sample we have some variation and uncertainty, so we need to add this uncertainty in our calculation. So in that case we don't from one sample we get mu hat as 8, but when we get another sample we can get mu hat as 7.5, let's say. So we cannot be sure that this obtained 8 can be obtained all the time. So we need to give some uncertainty, add some uncertainty to our estimation. Then we calculate interval estimation. So basically we are giving some range, small lower bounds and upper bounds, then subtract some quantities from our main estimators, and then this uncertainty, and then let's say we get our interval estimate for the mu value, our parameters, in a range. Another estimation type that we are mostly using is hypothesis testing. So basically we had some idea about our the value of a parameter, in this case hypothesis testing, and in this case we want to see the parameter value equals to some value like 8 or not, or it is smaller than 8, less than 8. So we try to do our hypothesis is correct. Which hypothesis is correct, the first one or the second one? Okay, so let me try to add a new page if it is possible. How can I do that? What is it? Okay, it's not. What is that? This is a text. Undo. Okay. How can I add a new page? Page. But it's not working. Okay. 1-to-1. What is this? Is the headers. This is the page numbers. Okay. Layout review view. Okay. What is this? Okay. So let me save this. Okay, so let me give this name as point estimation 1. I don't know how to get a new page. Okay, so if this works, maybe it's not working. Okay. Okay, so let me get a new page. Okay. Then let's continue. Okay, then here it's important to know what are the parameter space for us. Okay, so if we know our parameter space, so we know that where our parameters ranges actually. What is the minimum value that the parameter can take? What is the maximum value that the parameter take? Okay, so this part will be important for us. Not just the range of a random variable will be important, but here in this concept, the range of parameters will be also important to decide on the estimators. Okay, so the set of all possible values of an unknown parameters. Theta. Okay, so then we can say that our theta is in the parameter space. Okay, so when we consider a random variable from normal distribution, we know we have two parameters to be able to estimate. Then our parameter space will be for mu, our range is for a whole real line, and for sigma square all positive numbers. So this will be our parameter space. Then for this case, if both parameters are unknown, we are using this representation. Okay, so we have unknown parameters mu and sigma square. If both mu and sigma square unknown. Okay, and if we are writing in our PDF this way, then this means that sigma square is known here. It's not an unknown parameter if mu is unknown only. And similarly, if we write it like that, then this means that mu is known. Sigma square is unknown only. Okay, so these are some representations that we will use. If all parameters are not known, then we are representing our PDF as f of x, and we are adding these values. Sometimes we are writing them as conditional values because when x given mu, for example, we can define our parameter. Okay, so these two representations are the same. We will use this representation and Bayesian estimation. Because we need conditionals in that case. Okay, so in the estimation, our main problem is, okay, so we know the parameter space then, but when we have a sample where in our parameter space our unknown parameter theta is likely to be. Okay, so mainly we want to answer this question. So we have a family of PDFs. We will use this concept, family of distributions, family of PDFs, family of complete PDFs, family of exponential type. So we will have many different family of distributions in statistics, so we will learn those later. Okay, so but if we represent a family of PDFs, it could be exponential type, gamma type. This means that we know the form of the PDF. It's a gamma type or exponential or normal type. But there are infinitely many numbers for the parameters. Okay, so this for each theta we have one family, one of the member of the family basically. So when we consider all possible values of theta, then this means that we have a family of PDFs when we consider these infinitely many numbers. Okay, so it should be okay, so it's not like that. Oh, okay, so is it the new page? I hope. It's the mobile. Okay. Okay. So then, so our aim is to be able to choose. Okay, so this is not what I want actually, I think. Okay, let me use this. Okay, so it's not working either. Okay. Okay. Again, let me save this as point estimation 2. Okay, save it. Okay, so let me okay, so let me open new page. I need to find an easier way to do this. Okay, then our aim is to be able to choose an appropriate PDF from this family of PDFs. So this is known as an estimation. Okay, for example, okay, so we have a normally distributed random variable. Okay, so we have and let's say sigma square is known, then we represent our PDF this way with the unknown, the range of the unknown parameter. Then our parameter is theta is mu. We want to estimate it. What is our parameter space? Will be mu such that mu is in the plus minus infinity. Okay, and consider another example. Let's say we have a normally distributed random variable with mean, mu, and variance sigma square. And let's say in this time the two parameters are unknown. Then we have the PDF like that, and the ranges for the unknown parameters are like that. Then we have a vector of unknown parameters, theta in this case, and our parameter space as we defined before, we have mu and sigma square such that mu is in the real line, sigma square is a positive continuous variable. Then our point estimates will be theta hat, okay, equals mu hat and sigma hat square. So we have to replace parameters with some other thing actually. We usually use hats to represent them. So this is the point estimates of the unknown parameter. So if you write mu to represent an estimator, so it's parameter, it's not an estimator. So you have to use cap, tilde, or instead of mu you can use n. Okay, so just use different notation for the estimators. And one other thing actually, so the again there's a difference between estimates and estimators. If you remember, estimators are random variables. Estimates are numerical values of the estimators after we collect sample. Okay, so this is the difference between estimate and estimator. Okay, so when we have an estimator, theta hat, of an unknown parameter, theta, basically it should be a statistic Okay, so they do not have any unknown parameters because we are using them to be able to estimate the unknown parameters, but their distribution may depend on unknown parameters, which can be used for estimating theta. Okay, so since it's a statistic, as I told you, since it is a statistic, it cannot include any unknown parameter. But its distribution may depend on an unknown parameter. Like the sample mean. In sample mean x bar we don't have any unknown parameter, but it's this in distribution we have mu and sigma square over n, right? Unknown parameter. Okay. Let me save this again. Point estimation 3. Save. Okay, so let me stop here. I will continue with the estimation technique.